Hello, hello. In this lecture, we begin to look at the different changes that matter undergoes. When ordinary folks think about chemistry, boiling colored solutions and exotic reactions are what they picture. I can't blame them. That's what hooked me into studying chemistry. So if you've been doing the hard work of foundation and wall building in the previous lectures, congratulations. We're finally going to do some real chemistry and put all our knowledge about matter to good use. This lecture will be the first one in a series devoted to physical changes in matter. There's also a parallel series dealing with chemical changes. Okay, let's get to it.
A physical change will be defined here as a process linking one state of matter to another state, where the compounds in the system remain the same. What is altered is the temperature or pressure or volume or phase or a combination of all these physical properties. And though it can be argued to the contrary, we will treat dilute solutions and the process of dissolving compounds as a physical change as well, since it's easy enough to get our solute compound back by simply boiling away the solvent in solution mixtures. Most physical processes involve energy transfer in the form of work or heat and often are accompanied by changes in temperature. Before we begin, we need to review and be proficient in the use of units that quantify energy and temperature measurements. As discussed in another earlier lecture, temperature conversions between Celsius, Fahrenheit, and Kelvin are rather straightforward once you know the conversion equations. Now, up to this point, we've only mentioned measuring energy in the units of joules, so we'll need to expand our toolbox to include other energy units that are commonly used in chemistry. Again, the SI unit of energy is joules, which is equivalent to the SI base units of kilograms meters squared per second squared. A joule is a small unit of energy, and measurements in kilojoules can often be more common when talking about exothermic or endothermic processes on the molar scale of matter. Another energy unit used quite often is the calorie, which is at moderate temperature the amount of energy to raise the temperature of 1 gram of liquid water by 1 degree Celsius. Since a change of 1 degree Celsius is equal to a 1 Kelvin change in temperature, we can think about Celsius and Kelvin temperature changes as being, well, interchangeable. A calorie is about 4 times larger than a joule. The precise relationship between the two is 1 calorie equals 4.184 joules. This is an exact conversion. Even so, a calorie is still a very small bit of energy, so many times we scale this up by 1,000. 1,000 little calories equals 1 big calorie, which is commonly known as 1 food calorie, which is the energy unit we use on the back of food packaging. For example, in 112 fluid ounces of a sugared soft drink, there will be about 140 food calories, or 140,000 little calories. Another unit of energy that you might encounter, especially when you look at your electricity bill, is the kilowatt hour. This unit of energy is a derived unit that we will build in steps. First, we need to understand the concept of power. When looking at the specifications of electrical sources of energy, like a light bulb or coffee maker, they will have a power rating in watts. What is power? Well, let's say we have 2 dwarves picking apples and putting them into baskets. They are doing work which we can measure in energy units. Now, if one dwarf fills a basket twice as fast as the other dwarf, we say the fast dwarf is more powerful. Power is the amount of energy measured per unit of time. The power unit, watts, in SI units is joules per second. For example, a 60-watt light bulb puts out 60 joules of energy every second. So if we multiply the power in watts, which are joules per second, by time in seconds, then the time unit cancels and leaves us with energy. So if we leave a 60-watt light bulb on for 24 hours, how much energy will it have emitted or produced in the form of light? We simply convert our hours into seconds, knowing 1 hour equals 3,600 seconds, and multiply the seconds we obtained by the wattage to get the energy in joules, obtaining over 5 million joules. In the same way, we find that 1 kilowatt hour in joules will be equivalent to taking 1,000 watts, which is a kilowatt, and multiplying by 3,600 seconds, or a 1 hour of time. The conversion is 1 kilowatt hour equals 3.60 times 10 to the 6 joules, and this is also considered an exact conversion. To put things in perspective, if we were looking at our electricity bill, we would find that the cost of electric power would run us on the average about 12 cents per kilowatt hour, and the average electrical usage in the United States per household would be about 900 kilowatt hours per month. For our first physical process, let's look at the common procedure of heating or cooling a piece of matter. Assume the initial state of the matter is at some initial temperature Ti, and then we add or take away some energy from it. The material will typically respond to the energy change by raising or lowering its temperature to a final temperature Tf. The change in temperature is simply delta T equals temperature final minus temperature initial. Typically, if the delta T is negative, the substance is cooling. The temperature is decreasing. We have a loss in our energy, something akin to an exothermic process, and a net decrease in energy content in the matter. Typically, if the delta T is positive, the substance sees a rise in temperature. We have gained energy akin to an endothermic process, and we see a positive net energy gain by the matter. For moderate temperature changes, we can assume that the amount of heat energy absorbed or lost is directly dependent on the amount of matter and the extent of change in the temperature of the matter, delta T. This change should be an absolute result, in that if there is no temperature change or there is no material present, the energy absorbed will be zero. This simple fact of absoluteness allows us to rewrite our equation by simply multiplying the product of the amount of material and temperature change by a constant called the heat capacity of the material. This also allows us to replace the proportionality symbol with an equal sign. Algebraic rearrangement gives us a useful equation to measure the heat capacity constant of the material. Now, if we assume the energy absorbed is in SI units, then the energy measured will be in joules. The temperature change would be in Kelvin, though degrees Celsius is acceptable since temperature changes in Kelvin or degrees Celsius are equivalent. The amount of material can be measured in either moles or mass, such as kilograms, if we want to remain in SI units. The heat capacity is called a molar heat capacity if the amount of matter is measured in moles. If the amount of material is measured by mass, we call the heat capacity a specific heat capacity. The heat capacities in SI units for a variety of materials is shown in the table. You find in the first column the molar heat capacity, and in the second column is the specific heat capacities. It's also critical to note the pressure and temperature at which these heat capacities were measured, 1 bar and 298 Kelvin in this case. Heat capacities, like densities, are different at other pressures and temperature ranges. Heat capacity will be our linker in solution maps between the energy in or out of a piece of matter, the mass or moles of the matter, and the temperature changes the matter undergoes. It's our critical link in knowing just how much the temperature will change for that piece of matter when heat energy is added or subtracted from the material. Notice the specific heat capacities for the metals, such as silver, gold, or copper. These values are relatively low. They don't hold on to heat energy well and are used as heat conductors. Copper kettles and cookingware are very popular because they are prized for their efficiency and speed in transferring the heat energy from the burners directly to the food. This heat conduction property of a metal is in contrast to the specific heat capacity for an equal mass of water. Water can hold on and absorb great amounts of energy. Materials with high heat capacity values can be considered heat insulators. By the way, this heat capacity property for water is critical for life on this planet, which relies on the huge mass of ocean water to be able to modulate drastic temperature changes that might occur, attenuate their effects, and keep overall temperatures at moderate levels. Materials that are heat insulators are often used in the walls of our houses or in the making of coolers to keep our brews cool when we are playing on the beach. Let's do a few example problems that feature heat capacities. How much energy and calories will it take to elevate the temperature of 100 grams of water from 50 degrees Fahrenheit to 75 degrees Fahrenheit? Now, we immediately know we require heat capacities if we're heating bulk matter. Since we're dealing with a certain mass of water in the problem statement, it'll be easiest to use the specific heat capacity for water rather than the molar heat capacity. We find that the specific heat capacity of water is 4,178 joules per kilogram Kelvin at 1 bar and 298 Kelvin. Now we're going to make a reasonable assumption that this value is constant throughout this temperature change. We want the calories of energy used to heat up the water, and we're starting with 100 grams of water in our solution map. To use the heat capacity, we want our temperature change to be in Kelvin or degrees Celsius, so we will quickly convert our temperatures from Fahrenheit to Kelvin. 50 degrees Fahrenheit equals 283.15 Kelvin, and 75 degrees Fahrenheit equals 297.04 Kelvin. The temperature change will be 13.89 Kelvin, where we have underlined the 3. See, don't forget to keep track of your sig figs at every step, and as always, avoid rounding off your numbers till the very end. Notice how we use the heat capacity to cancel the mass and temperature units, and how we use the calorie-joule conversion at the end. So plugging everything in, it looks like we will need 1,400 calories of energy to raise the temperature of the water. Here's another example. We have 25 grams of silver at 112 degrees Celsius, and it loses energy, minus 500 joules of energy, due to energy transfer. What is the silver's final temperature? Remember, if we lose energy, the sign of energy must be negative, and if we gain energy, it will be positive. We calculate the temperature change by first starting with the energy lost per gram of silver. From there, we can get to the temperature change by converting the mass to kilograms and dividing by the specific heat of silver. As always, the ratios are arranged in a way that will cancel the units. Since we know the initial temperature, the final temperature is easy to calculate now that we know the temperature change. The most critical value we need in the computation is the specific heat of silver, which is 230 joules per kilogram Kelvin. Plugging it all in, we get a negative minus 87 Kelvin change, which again is the same as a minus 87 degrees Celsius change. So, the final temperature will be 25.0 degrees Celsius.
We have now taken our first step into the world of physical changes. Now, it turns out that measuring temperature changes in a reference piece of matter, such as water, in an experiment called calorimetry, is one of the chemist's favorite tricks when capturing and measuring energy changes of all kinds of processes, physical and chemical. It's also important to know that heat capacity values are critical in thermodynamics when we compute the important quantities such as entropy, delta S, and enthalpy delta H, or in predicting how reactions will run at various temperatures. Hey, and this was just the first lecture in this series dealing with physical processes. Catch you soon in the next video on physical changes.